You see it? Okay, hopefully you can see my shared screen. Today, sorry. So thanks for having me. My name is Eitan, and I'm a postdoc at Northwestern University working with Ken Kaller. Today I'm going to talk about made together, replay together, the role of encoding context in memory reactivation during sleep. So some background for those of you who are not in the sleep research world. Memory consolidation is thought to happen through reactivation. Specifically for declarative memories, we believe they are supported by these neocortical hippocampal circuits represented here in this graphic as these kind of nodes in the neocortex and hippocampus. And after encoding, during offline periods, and specifically during sleep, you have this consolidation process that is thought to be achieved through reactivation, in which these nodes communicate with each other. Typically what we would have is this cortical hippocampal cortical loop, such that a cortical node would reactivate the hippocampal node, which thereby would reactivate other hippocampal nodes. And the consequence of this is this cementing of the cortical networks and creating of a cortical network. So that later in retrieval, there's a lot of debate about what the role of the hippocampus is, but what there is no debate about is that the hippocampal circuits are strengthened and cemented through this process. And this happens primarily, or we don't know if primarily, but sleep has a lot to do with this process. So let me talk just really briefly about sleep for those of you who are not from this world. So as you probably all know, sleep is divided into different stages, going from wake to the deepest stage of sleep, termed N3 or slow wave sleep. If we were to look at the EEG signal, this would be an EEG signal during wake, and during sleep, during slow wave sleep, the deepest stage of sleep, it might look something like this. So these high amplitude, low frequency waves that define the slow wave sleep. And on top of these slow waves, you would see these faster activity patterns called sleep spindles. And right now, our understanding is that these complexes of slow oscillations and sleep spindles together, their combination is what supports this process of memory consolidation. And we'll come back to this later on in some of the slides. So encoding and retrieval and consolidation in the middle, but for most of us here at this symposium or this conference, what links encoding and retrieval most of all is context. And we talk about context in a lot of different ways, but I think probably the easiest and best, or one of the best examples of context at play can be seen through this contiguity effect. So in a free recall task, participants are more likely to remember these clustered of words that were remembered one next to each other. So if a certain word was remembered, a word that was encoded just next to it in temporal proximity is more likely to be remembered, to be recalled next. And the idea here is that when we retrieve a certain word, we mentally time travel to the time of encoding, and that brings about these memories that come together within that temporal context. Or to frame it quite simply, retrieval or a retrieval queue initiates context reinstatement, and that in turn initiates retrieval of contextually linked items. And today I want to try and explore what consolidation has to do with this process. So maybe a bit about context and memory reactivation, or context and sleep more specifically. So there is some evidence that suggests that sleep binds items and their encoding contexts, but there's very little literature about trying to explore the question of whether memory reactivation during sleep itself involves context reinstatement. And that's what we wanted to do here. We wanted to see if, like during wake, you would see this retrieval, context reinstatement and retrieval of contextually linked items. Is it also true that during sleep, you would have reactivation of a certain memory that would in turn lead to context reinstatement and reactivation of contextually linked items? That was the hypothesis we came into the study with. And we think that if this really happens, the reactivation of one memory would entail the reactivation and consolidation of others that share its context. So enough of background, let's talk about what we did here. So I'm going to present two experiments today, and they both follow the same basic design or same basic task, which I'm going to introduce now, and then I'm going to go into the details of each one of the two experiments. So the task started with participants having to build a story using a scene, an image of a scene, and 4 smaller images of objects or animals or other smaller items. For example, for this scene, the story that the participant might build might be in the jungle, a cat with a lighter in its mouth was playing volleyball, and the ball flew off and hit a big gong. So they can build their own story however way they want, and they do this for a bunch of different scenes and a bunch of different items, 4 items per scene. After they're done building these stories, we go to a different task with these exact same items. So in each one of these learning blocks, there will be 8 items, 4 for each of the 2 scenes that are represented in the block. So each block includes 2 scenes and 8 items. They had to just learn the location, the positions on the screen using this this grid of these different items. Just where do they go? Where are they on the grid? And they have to keep learning until they reach some criterion. And we had a bunch of these different blocks, each one including 2 of the scenes. And these items were kind of intermixed together one with the other. Importantly, while they were doing this task, we kept asking them questions about their stories, about how the items fit into the story. So we kept kind of reminding them of the stories and reminding them of the what I'm going to call semantic context, or the context that binds the scene with the different items. So again, different blocks, each block with 2 scenes, each scene with 4 items. And for the purpose of today's talk, I'm going to consider these blocks as a proxy of temporal contexts, because these 2 scenes were learned in a different block. They kept being repeated over and over again in a specific temporal time frame. And the scenes are, the stories that are related to the scenes are going to act as semantic context. They also share temporal context, but importantly, they only the scenes share the semantic context, whereas the blocks have these 2 different scenes with 2 different stories. So the first experiment I'm going to show you is a sleep versus wake study we did using an app that we designed. So participants did this at home. It was a between subject design. And participants first build the stories and learn the positions, and then were tested after a delay. And that delay, crucially, either included wake or sleep. So this is what is termed often an A and PM study. We had 2 different groups, one that had sleep and one that had wake, with similar delay lengths. And what we were interested here was asking, does context impact how memory changes over time? So you can think of these 2 extremes. So these are 4 items that all belong to the same scene. And you can think of a spectrum between high clustering and low clustering, where high clustering means that all these items, their trajectory over the delay are pretty much the same. So you can see these different green lines are pretty correlated one with the other. We would call this the high clustering side of the spectrum. And that would mean that items that are contextually linked to each other also share memory trajectories, which might mean that they're reactivated together, or reactivated together more than you would expect by chance. And low clustering would mean that every item would go every other way, and that would mean that context doesn't explain any of the variability in the trajectories for these different items. So our predictions and our hypothesis was that the variability in memory benefits over sleep will be explained by shared context. And more specifically, we believe that sleep will have higher clustering than chance, and sleep will have higher clustering than wake. And here is the data for this study for the semantic context. So now we looked within these stories. We have 4 items, or 4 items within a story, and we can look at the intra-class correlations between these different items, among these different items actually, and compare each actual distribution shown here in the left in black with the what we would get by just shuffling items around with a permutation test. And we see that indeed in the sleep group, you see this higher than chance clustering, higher than chance interclass correlation coefficient, meaning there's shared trajectories. You don't see the same for wake, and there's a significant difference between sleep and wake. We did the same thing for the temporal context. So now we looked not only at these stories together, but at the blocks that included two different stories together, and saw whether temporal context explains any of the variability we see over sleep or over wake, and it does not. So we do not see any above chance ICC or interclass correlations here, meaning that memory benefits are not correlated between items linked by temporal context after sleep. So this was a cool finding, and we wanted to follow this up with more of a causal manipulation of memory reactivation. So here we just looked at the trajectory and the changes over sleep. But to causally manipulate reactivation, we used a paradigm called targeted memory reactivation. And put simply, the idea here is that just like I showed you this consolidation pattern of interactions between the hippocampus and cortex during sleep, with TMR, with targeted memory reactivation, we basically bias consolidation for certain items. And we do that by unobtrusively presenting stimuli that are related to different memories. For example, we can present a sound that is related to a certain part of the memory, and it would reactivate the whole circuit and bias that memory towards more reactivation. And the classic study that shows that uses this design would be one that has this spatial task, different items in different locations, and you would hear congruent sounds such as this cat's meow. And you would learn all these different items, then you would go to sleep, and then the deepest stage of sleep, in slowing sleep, you would hear these sounds presented unobtrusively, sounds related to some of the items but not others. And the classic finding is that you would see less forgetting for these items that were cued, showing that even though the participant does not remember hearing these sounds, they bias memory reactivation and consolidation during sleep. So that's so we use this manipulation and we overlay this on top of the same basic design. So here, taking this block, for example, we have these 8 items divided into 2 scenes. What we did is we presented sounds related to 2 of the items related to one of the scenes. So I'm going to present this differently so it will be maybe clearer. We have 2 scenes. For one of the scenes, 2 sounds were presented and 2 weren't. And for the other one, none of the sounds were presented. And then we also have blocks in which none of the sounds were presented at all. And what we achieved by doing this is that we could compare cued items within cued scenes. This is the classic TMR design of just cueing these individual items and seeing them improve, and they did, as we'll see in a second. But importantly, we'll also have this distinction. We'll have in the red, we'll have these uncued items within a cued scene. In other words, these items share the semantic context, but they weren't cued directly. And we would have uncued items that were not within the cued scene. So there's no shared semantic context. And we were wondering what would happen to these red ones. Those are the ones of interest today, to see whether they indeed improved as well. And that would mean that context itself was reinstated during sleep. So this is a result from one of the participants. There are 29 participants. I just wanted to show you a single participant data, which I like to do. And these are the overall lines that we see using a mixed model looking at all participant data. And what we see in all these plots is on the x-axis, we see the pre-sleep error. On the y-axis, we see the post-sleep error. Those are obviously correlated. The items you got best before, you'll get best after. That makes sense. But importantly, the higher the slope, the more forgetting you would get. And you see this higher slope for the uncued items that do not belong to cued scenes, and the lowest slope for the cued items in the cued scenes. But importantly, for our purposes, this red line is right smack in the middle, and the interaction is significant, and so is the difference between the non-cued items and the cued items. The uncued items in the cued scenes. So that means that cueing benefits memory not only for reactivated memories, but also for contextually linked memories. And then we looked also at semantic context. So I'm gonna, again, look here on the left to kind of divide it. So these uncued items in a queued scene share semantic and also temporal context. But then I can look differently at these unqueued items that don't share any context, and these items that are within the same block. So they share temporal context with the items that were queued, but not semantic context. And again, this helps us test whether temporal context plays a role during sleep. And again, our results, so you can't even see it because the blue and the purple line are one overlaid on top of the other and no differences. So what we found here, again, just like in the purely non-manipulated results, we see that temporal context does not impact reactivation consequences at all. So interim summary, just looking at the behavioral results, and then I'm going to dive into some neural results. So memories that share semantic but not a temporal context are reactivated and consolidated together during sleep. And this is actually in line with a cool study that came out just this year from a Charan Ranjanath group with a completely different aim and design, but similar results. So what they found was that semantically related memories that were learned at different times were binded together by sleep. So you can see this here on the right. So these are related memories, semantically related memories that were learned temporally far one from the other, and you can see in the green that sleep improves their binding together, whereas relative to wake. But the same was not found in their study for semantically related, but semantically unrelated items that were learned temporally close together. So again, they didn't find that sleep has anything to do with temporal context. This is really interesting. Cool. I'm going to dive into some neural results in the last 5 minutes or 6 minutes, whatever I have left. We wanted to see what the role of slow oscillations and spindles are in this contextual effect of reactivation. So here on the left, I show you results from electrode CZ, and these are time frequency results. For those of you who are not familiar, on the x-axis, you can see the time relative, in this case, to sound onset during sleep. So time 0 here is when the sound started during sleep. On the y-axis, you can see frequencies in hertz, and the colors represent changes relative to baseline in frequency. So you can see this large, vast increase in lower frequencies about a bit less than a second after sound onset during sleep. This is for all the sounds that we presented across participants. And you can also see this kind of area here, and these are basically this is where the sleep spindles happen. So these are the two clusters that came out as significant, and the higher frequency one corresponds to sleep spindles, lower frequency one corresponds to slow oscillations. We were wondering how we can test whether these two have anything to do with the results I showed you previously regarding context and sleep. So here's the analytic approach we used for this analysis. Imagine these two sounds are presented that are related to scene A, the cat and the lighter. And then there's a different sound related to a different scene, such as this cow that's related to scene B. What we wanted to see was look at these waveforms. I'm showing spindles here, for example, but we looked at all of them, and try and see whether they are correlated within context or within scene. In other words, does the power for the spindle following a cat sound correlate more than with the power of the spindle for the lighter sound than it does for something from a completely different scene. So if indeed we see, so these are completely different sounds and we arbitrarily define them as related to a single scene. This was manipulated completely. So if we do see these correlations more than we would expect based on these correlations, then we could probably tell that there's some contextual thing happening during spindles. The null hypothesis, of course, being that these are all randomly drawn from some distribution regardless of the scene association. What we did was we looked at these different clusters that we found significant. In the spindle cluster, we divided into two clusters just because typical spindles usually happen a bit later, after 1 second after sound onset in previous studies. So we looked at the whole cluster and also divided it into 2A and 2B. And our first finding was that, again, using interclass correlations, post-Q spindle and these are these ones, especially the light gray one, which is cluster 2, and the blue one, which is 2b. So these two are correlated within scene more than you would expect for them to be by chance. Again, we did a permutation test with intra-class correlation, so it does show that these spindles are more correlated within a scene than they are between scenes. And then, importantly, this predicts behavior. So this predicts behavior for performance or change in memory for the queued items. As you can see here, so this shows forgetting. So bottom is better and upper is worse for the y-axis. Now the x-axis, you just see the ICCs. So here you see that it does predict the behavior quite well for the queued items, but crucially, it also predicts only the 2B cluster predicts changes in performance for the unqueued items in the queued scenes. So this basically means that it predicts the contextual effect, which it was we were very happy to find this. The last analysis I'm going to talk about today in the last few minutes is looking more directly at reactivation during sleep. And to do this, we used a correlational approach, but something a bit different. So first, we identified neural patterns that are involved in wake scene processing, because we used the fact that these are scenes that we're looking at, or scene-related contexts. And then we looked at these patterns and tried to see whether they are reinstated during sleep. So before any of those tasks began, we had participants do a simple one-back task, just looking at faces and abstract images and scenes or places. And we, based on these data per participant, we averaged and found the response pattern in the EEG for these three different groups. Just to show you that when we use a SVM classifier, they are easily distinguishable. We can tell quite well from the EEG data whether participants are looking at abstract images or scenes. And then we use these patterns, specifically the scene patterns, and correlated these with the data during sleep. So here's how that looked like. For example, if we were to take the activity pattern 1 second after scene onset, and it will be this, and correlated with the pattern of activity 1 second after sound onset during sleep. This would be the pattern. We would have a single correlation metric, and it would map on to this point in the plot that I'm about to show you, and we will show you, I will show you the full plot with all the different correlations with different time ranges for both wake and sleep. So this is the pattern we would see for places. So you see this kind of burst of correlation happening about 1 second after sound onset during sleep. But we were happy to see this, but then we saw that we see pretty much the same pattern for the abstract images, which means it might be just some similarity to general wake EEG activity. So we use the subtraction to find the scene-specific activity. So this is place minus abstract, so the subtraction between these two, and we still see this nice activity, so nice scene-specific correlation between wake and sleep. Importantly, it doesn't happen only after sleep, after the sound onset at time 0 here on the y-axis. It happens throughout the whole thing. So we see scene-specific neural representations that are reinstated by cues during sleep. And because I'm running out of time, I'm going to just briefly say that this correlates also with behavior, but only for the queued items, not for the non-queued items. Unfortunately, that would have been cool if the contextually linked items that benefit, as I've shown before, if that would have correlated. It does not, but the queued items themselves are correlated with this burst in activity that you can shown here in yellow. So it predicts benefit for queued, but not unqueued items. So I'm going to sum up. So memories that share a semantic but not temporal context are reactivated and consolidated together during sleep. I've covered this in the interim summary. And now we've shown that post-Q spindle spectral power is correlated with in-scene, and that this correlation predicts contextually determined benefits. And finally, I showed you that scene-specific neural representations are reinstated by cues during sleep, and that this reinstatement predicts benefits for cued memories. And if you have to just take one message home from here, it will be that memory reactivation during sleep involves the reinstatement of semantic context, consequently impacting consolidation. And I'd like to thank my lab members and collaborators who were instrumental in this work. And thank you for listening. Open it up for some questions.
Thank you, Eitan. So probably have time for just one question. Does anyone have one burning one that they would like to ask?
I have one. Could you talk briefly on the ICC measure that you used as the dependent measure for the earlier study?
Sure. So usually we use interclass correlations. We call them just correlations. So correlation between height and weight, for example. So that would be all two vectors, one only heights, one only weights. But what would happen if you want to correlate two things that are from the same group? The classic example would be twins. You want to correlate height between twins. You can't just choose one twin to be the x-axis and one twin to be the y-axis, because that would be arbitrary. And you can't say, okay, I'll take the first. I mean, you can't really think of any way the correlation would make sense between something that is equivalent. So intraclass correlation developed back in Pearson's day, with the same time that the classic correlations we all use were developed, overcomes that by having this symmetrical measure, and later on was developed to include more than two items, so several items within a group. And the idea here is that, for my purposes, is that I have these 4 items, so a quadruplet of items, and I can't really put any of one of them and correlate with the other in any non-arbitrary way. So I'm looking at how much of the variability is explained by the within group variability versus the overall variability. That's basically what ICC does.
Great, it's good work, thanks.